Quantum computers are a new type of computer that operate on the principles of quantum mechanics. Unlike classical computers, which use bits, zeros and ones, to represent information, quantum computers use quantum bits, or qubits, which can exist in a state of superposition, meaning they can represent both 0 and 1 at the same time. This property of superposition is what gives quantum computers their power. By manipulating the qubits, quantum computers can perform certain calculations much faster than classical computers. This is particularly useful for problems that involve large amounts of data or complex algorithms, such as cryptography, optimization, and simulation. One of the most famous quantum algorithms is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. This has significant implications for cryptography, as many encryption methods rely on the fact that factoring large numbers is difficult for classical computers. However, quantum computers are still in their infancy and face significant technical challenges, such as maintaining the fragile state of the qubits and minimizing errors. As a result, quantum computers are currently limited to small-scale experiments and simulations, and it remains to be seen how and when they will become practical for real-world applications. Working of quantum computers. Quantum computers are a type of computer that use quantum mechanics to perform computations. Unlike classical computers, which use bits to represent data, quantum computers use quantum bits, or qubits, which can represent multiple states simultaneously. The basic unit of a quantum computer is a qubit, which can be implemented using a variety of physical systems, such as superconducting circuits, trapped ions, or photons. The state of a qubit can be manipulated using quantum gates, which are analogous to the logic gates used in classical computers. One of the key properties of quantum computers is entanglement, which allows two or more qubits to become correlated in a way that cannot be explained by classical physics. This property allows quantum computers to perform certain computations much faster than classical computers. One example of a quantum algorithm is Shor's algorithm, which can factor large numbers exponentially faster than classical algorithms. This has important implications for cryptography, as many encryption schemes rely on the fact that factoring large numbers is computationally infeasible. However, building a practical quantum computer is a significant technological challenge, as qubits are highly sensitive to their environment and are prone to errors due to decoherence. Researchers are actively working on developing error correction and fault tolerance techniques to overcome these challenges and build practical quantum computers. Quantum computers consist of several parts, each of which plays a crucial role in their operation. Here are some of the key parts of a quantum computer. Qubits. The basic unit of a quantum computer is the qubit, which is the quantum analog of a classical bit. Unlike a classical bit, which can be in one of two states, 0 or 1, a qubit can exist in a superposition of states, allowing it to represent multiple values simultaneously. Quantum gates. Quantum gates are analogous to the logic gates used in classical computers. They are used to manipulate the state of qubits and perform computations. Examples of quantum gates include the Hadamard gate, which creates a superposition of states, and the CNOT gate, which performs a controlled NOT operation on two qubits. Quantum registers. A quantum register is a collection of qubits that are used to store information. In a quantum computer, registers can exist in a superposition of states, allowing for massive parallelism in computation. Quantum circuits. A quantum circuit is a sequence of quantum gates that act on one or more qubits. The circuit represents a quantum algorithm or calculation. Quantum memory. Quantum memory is a component that stores quantum information, allowing it to be accessed and manipulated at a later time. The development of efficient quantum memory is a critical challenge in building practical quantum computers. Quantum processors. A quantum processor is the physical implementation of a quantum computer. It consists of qubits and associated hardware that allow for the manipulation and control of the qubits. Quantum error correction. Quantum error correction is a set of techniques used to detect and correct errors that occur due to decoherence and other sources of noise in quantum systems. These techniques are crucial for building reliable and scalable quantum computers. These are some of the key parts of a quantum computer. Each of these components plays a critical role in enabling the powerful computational capabilities of quantum computing. Quantum computers perform tasks using quantum bits, or qubits, which can exist in a superposition of states, allowing them to represent multiple values simultaneously. This property of qubits enables quantum computers to perform certain types of calculations faster than classical computers. Quantum computers operate using quantum gates, which are analogous to the logic gates used in classical computers. These gates are used to manipulate the state of the qubits and perform computations. Different types of gates are used to perform different types of operations on the qubits. Quantum algorithms are designed to take advantage of the unique properties of qubits and perform specific tasks more efficiently than classical algorithms. For example, Shor's algorithm is a quantum algorithm for factoring large numbers, which is believed to be intractable for classical computers. Grover's algorithm is a quantum algorithm for searching an unsorted database, which is faster than the best-known classical algorithms. To perform calculations, quantum computers use a process called quantum parallelism, which involves operating on all possible values simultaneously. This allows quantum computers to perform certain types of calculations much faster than classical computers. However, quantum computers are also susceptible to errors caused by decoherence and other sources of noise, which can cause the qubits to lose their coherence and produce incorrect results. To address these issues, researchers are developing new techniques for quantum error correction, which involves detecting and correcting errors in quantum systems. Overall, quantum computers perform tasks using qubits and quantum gates, taking advantage of the unique properties of quantum mechanics to perform certain types of computations faster than classical computers. Quantum computers offer several advantages over classical computers, including speed. Quantum computers are capable of solving certain problems much faster than classical computers. For example, Shor's algorithm, a quantum algorithm for factoring large numbers, can solve problems that are believed to be intractable for classical computers. Parallelism. Quantum computers can perform many calculations simultaneously due to the superposition of quantum states, allowing for massive parallelism in computation. Optimization. Quantum computers are well suited for solving optimization problems, such as the traveling salesman problem, which involve finding the best solution from a large number of possible solutions. Cryptography. Quantum computers can break many of the cryptographic systems used to secure data on classical computers. However, quantum computers can also be used to create new, quantum-resistant cryptographic systems. Simulation. Quantum computers are ideal for simulating quantum systems, such as molecules and materials, which are difficult or impossible to simulate using classical computers. These advantages make quantum computers potentially useful for a wide range of applications, including drug discovery, financial modeling, and machine learning. However, building practical quantum computers remains a significant technological challenge, and many fundamental questions about the capabilities and limitations of quantum computing remain unanswered. While quantum computers offer many advantages over classical computers, there are also several disadvantages and challenges associated with quantum computing. Here are some of the main disadvantages of quantum computers. Fragility. Quantum computers are highly sensitive to their environment and are easily affected by even minor disturbances. This can cause errors and make it difficult to maintain the coherence of the qubits. Complexity. Quantum computing is a highly complex field, and developing algorithms and building practical quantum computers requires expertise in physics, computer science, and mathematics. Limited applications. While quantum computers are ideal for certain types of problems, they are not necessarily faster for all types of computations. Many problems that are easy to solve on classical computers may not be well suited for quantum computers. Scalability. Building a large-scale quantum computer is a significant technological challenge. As the number of qubits increases, maintaining coherence and controlling the interactions between qubits becomes increasingly difficult. Cost. Building and maintaining a quantum computer is expensive, requiring specialized equipment and a significant amount of energy. Security concerns. While quantum computers offer many advantages for certain types of applications, they also pose a potential threat to security. For example, quantum computers could be used to break many of the encryption systems used to protect sensitive data. These are some of the main disadvantages of quantum computers. Despite these challenges, researchers are working to develop new technologies and techniques to overcome these obstacles and build practical quantum computers that can take advantage of the unique properties of quantum mechanics. Thanks for watching.